driving in the respective photographs. Yeah. Well, if we all around and walk the ocean, well, not qualified for that. That's why I said
Hey, how are you? Alright. I need to just introduce you. Yeah, this is the catering. Okay.
Yeah, I'm Caitlin. I'm just grading for this class, so this is what I look like. You probably won't see me around here though. I usually
Yes,
work from
she's
home.
the one primarily responsible for grading the homework. And I think if you have questions about homework related things, particularly about grading, definitely you contact her. But for some of you feel more comfortable contact us for help, also reach out. I think that we will also valuable resource. Okay. Yeah, that's really good. And she did this last year for me, so she's excellent.
Thank you.
And third year?
Fourth year now.
Fourth year now. So also anything about the graduate student, I'm sure she's more than happy to provide people. But thank you, stop by.
Alright, thank you. Today.
Yeah, where's the first guy?
Alright, good morning everybody. How are you guys doing?
Still alive.
You doing well? I'm going to stand on this side. I have that recording going on. Just want everybody to know that recording is going on, so I hope you don't object. That's our let you know. Anybody have questions before we start? Any specific questions? General questions? No? Alright. So last time we talked about base and representation, right? Today, alright, so now we're going to, and I think I did start talking about measurable, observable, measurement of observable, right? So let me pick up from there. So once we choose a base, the base basically is a complete set of eigenstates of certain operators. Right? So if you have a base, then we say any arbitrary quantum mechanical state can be written as superposition of a base state, right? And this coefficient, example, prime coefficient is just the prime of prime. So that is CA prime. And remember this CA prime square, F length square, is interpreted as the probability of finding a prime state in a object state R. And this is general interpretation of the inner product of two object states. Can be interpreted as finding the probability of finding A state in alpha state in beta state. Is this same thing as finding the probability of beta state in A state in alpha state? Are they same? Yeah?
I think you said last time that they were.
They were. Can you see it from here why it's the same?
Yeah, so it's that times its conjugate, and the beta of alpha is just
It's the same one. So
yeah, so
because this
conjugate
is absolute magnitude plus which of this quantity is exactly the same. Right? Exactly the same. Now, when we do measurement, we basically say if you have alpha state or some object state, if we do a measurement, and let's call this measurement A, which is associated with operator length, this always collapse into a particular quantum mechanics state, which is a eigenstate of the operator you do measurement, and with the probability, because with the probability of CA prime, which is square, which is of course is this A prime. So that's what the measurement does. The measurement causes the quantum mechanics state to collapse into a particular eigenstate. I'm going to define a expectation value in general, this is notation. The expectation value of observable, some observable A, okay, in a quantum mechanical state alpha is formally defined as this. And this is just the definition of the expectation value. And intuitively you think, basically say this is the probability of finding this with a particular A prime value, and therefore one would expect this cost. Yeah. And one would expect this expectation value to be a sum over A prime. This is probability, therefore it will be this, and then that value will find that is A prime. That is associated probability, so add together, that would be kind of expectation value or average value. Yes.
I'm sorry to interrupt. Can you please, I can't really read what you've written on the third line on the left.
Is it too low?
No, well, that line there, yeah. What is that?
Measurement.
Oh, measurement.
A measurement which is associated with a operator collapse into a quantum mechanical state.
Yeah.
But can you see it here, one line here?
Yeah, it is. I mean, it is kind of low, but that's just because I'm sitting in the back, so
Okay.
I wanted to better sit in front. I suppose.
Yeah. So then one would expect this, right? So, and in fact, indeed, you can see this. That's substituting this alpha into here. So this is the bronze. So therefore, this will be sum over A. Let's call A prime. Blah A prime, and this will be C A prime. With the C A prime, if I take a dual space of this, what it will be? It will be A prime or A prime, C A prime will go to what?
C A prime star.
Star, what is equal to star. And then I have operator A here. And then I have just some double prime. So this will be C A double prime, right? In general, this two indexing are different. They're done in vertical. So now I'm going to just simply widen these things to be here. This contact is so sum over A prime, A double prime. Right? Good? Now, because this A, C A prime, C A double prime are C number, so I can kind of pull this out. C A prime, this is the star, C A double prime, and have A prime, operator, A double prime. Yeah? Very good. And what this quantity is, remember this A prime, A double prime are eigenstates of operator A, so therefore this will give me A prime, A double prime, A double prime. Yes? Okay? And of course this A double prime can be pulled it out, so this will be sum, this will be C A prime, C A double prime, star here, A double prime, and this is A prime, A double prime. Yeah? Follow? Somewhere a lot? Okay? And what this quantity is?
It's delta A prime A double
That's
prime.
delta, right? That's orthogonality of eigenstate, right? That's orthogonality. So therefore, one word summation disappears, so this now becomes sum over A prime, A double prime has to be E A prime. So therefore, this is C, this is A prime, or A prime, star, A prime, A prime. Yeah? And that's exactly what we have here. So intuitively, that all makes sense. Right? So expectation value, because if I do a measurement and it has many possible values of the measurement, and I could obtain measurement of this value, associated probability is that, and then sum over all that, that's kind of the average value, and that's what we call expectation value of the observable in that quantum mechanics state. Let's do an example of this. Right? Let's do an example of this thing. So let's say our wavelet. This of course sometimes we write on this following here. This fine. This would be okay to be write on this. So this is a prime. Okay, this is just complete same notation. This is a prime. So let's say the favorite example as Z operator. Right, that is our A operator. Let's say our alpha state is happen to be plus state. Right, and remember this in the basis of a Z operator, this in terms of matrix notation, that's a column vector. And in the basis of its own eigenstate, a Z, remember, is 1, 0, 0, minus 1. That's one way to write it. Right? Okay, good. So, obviously, of course, a C operator on plus is h bar over plus 2. Right? If I do expectation value, which is this notation, and that of course will be formally alpha, that's C alpha. Right? And in this simple case, this is plus C plus. Of course, you would expect in is equal to h bar 2 because my state is happen to be an eigenstate of the C operator, and therefore, if I do measurement, I'll find that particular eigenvalue with 100% probability. With 100% probability because, right? Because C plus in this case, of course, it is plus alpha, and my alpha happens to be plus. So therefore, that is 100% probability. Right? That's trivial. Now imagine I'm using the same basis. But my alpha state is supposed to be Sx, being oriented on the XX plus state. And that, for last time we did, right, we did the exercise. Last time we said this can be written as 1 over square root of plus superposition minus. The basic notation is 1, 1. Yeah. So 1, 1. Now, what would expect the expectation value? Remember, we did this Stengara experiment. If my state is in Sx plus and I do a Z measurement, I get 50% to get plus and 50% get a minus. Right? So I would expect that one. So therefore, if I do measurement now in this case of the SC operator in this state, I would expect expectation value to be, of course, I have a 50% of probability producing h bar over 2, right? And I also have 50% probability to producing h bar minus h bar over 2, right? 50%, that's the, and in fact this is equal to 0. Right? So if you do a Z measurement, now you can kind of see this directly here. In fact, let's see that. So formulate as C. Yes? Somebody don't mind, turn my video cameras on the other side for. So if I do that, I will get this will be formulated up. So this will be Sx plus Sc Sx plus. Right, that will be a notation. And the Xx plus, remember this is Xs, this is a cat, blah will be transpose and a complex conjugate. So this will be transpose and a complex conjugate. That will be Sc in matrix notation. It's here. So it's h bar over 2, 1, 0, 0, minus 1. Sx plus is square root 2. 1, 1. Right. And I'd like you guys to multiply all this matrix. So coefficient wise, this will be h bar over 2 if you multiply these two matrices together, what do you get? Do it on your own, do it yourself. What would you get? You multiply those two matrices together. Yeah. The corner, somebody. Ethan family?
Yeah.
Ethan?
Repeat the question.
Huh?
Can you repeat the question?
I multiply these two matrices together. What do I get here?
You'll get 1 -1.
1, -1? Yeah?
Isn't it going to be just a column matrix?
Okay, so is 1, -1 exist?
I think so.
Okay, agree? Yeah? Good? Alright, very good. And now we multiply this together.
We need a constant, I think.
Huh?
I think we need to multiply the last two constants in too. It's not going to matter, but we do need
So
them.
this would be force, is that right?
Yeah.
Yeah, very good, very good, very good. Now we multiply this together, what do we got? Alright, 1, 1, 1 minus 1, 0, right? Just conform to what we expected here. Okay, so this is just the intermediate matrix notation what to expect. And so obviously when we write on this form, we say you have 50% probability plus 50%. The same thing. Remember we did that with x minus. This would be square root of 2 plus minus. This. We did that. So I will not review this stencil. Now, if I do sy, and then from Stern-Geller experiment, we know sy plus, if we do the measurement, we also producing 50% plus and 50% minus. So say, genetically, most, this must be has a form of this way. This is most general form, which you would produce 50% probability on plus, 50% probability on minus. This can be off to your face. I cannot choose this delta equal to 0 because that is already Sx plus. Neither I can choose delta to be pi because that is x minus. And now we need to enforce the fact that the xx and the sy are different. Right? They are different. They are incompatible or observable. In fact, if we do Stern-Geller experiment, suppose I prepare a state in xx plus, and then if I do sy measurement, we know from Stern-Geller experiment you get 50% sy plus 50% sy minus. So one would expect if my alpha state is xx plus, right, and I do sy measurement, that probability would be also have to be the average of that has to be 0. The average of that has to be 0. So we would expect that if I do x, for example, x measurement, and in sy state, the probability, this is the probability amplitude of finding xx plus in sy plus. This square is the probability. From experiment, we know this must equal to half. If that must equal to half, let's just multiply these two things together. If we multiply these two things together, what would we get? So if I actually calculate this quantity, this will be square root 2. Square root 2 multiplied square root 2, so this will be like, we say it's 1 minus 1 e to the I delta, right? E to the I delta. And now I want this whole thing to be squared. This whole thing squared, it will be quarter. It will be 1, 1, 1 minus e to the I delta. And then we want the absolute magnitude of this thing to be squared to be half. If I enforce this to be half, the only solution of this delta is plus minus pi over 2. But if it is a plus pi over 2, this will be e to the I pi over 2, e to the I pi over 2 is, so in that case this would be 1 plus, minus plus. Did I? This is x plus. This is plus sign, right? That's plus sign. So in that case, this will be plus minus I, right? And a absolute magnitude square of that is square root of 1, square root of 1 and 1, so it's square root of 2, and then you square it, and you get 2. That's all that you have. So if I choose this will satisfy that relationship. So convention is then choose the plus pi over 2 for sy plus, so therefore sy plus will be formally written as plus I minus, and the sy minus is equal to 2 and the plus minus I. And this will be the matrix notation is 1 I, this matrix notation is 1 minus I. Very good? So that's kind of intuitive. Then with that, now we can get the matrix representation of XX operator and SY operator. So XX operator now, got to the state, we know is SX operator, of course, can be written as H bar over 2 as X plus. This, remember, is a projection operator. This is an outer product. And then it's also a probability to minus H bar over 2, X minus, right? And then use this matrix notation we have here. We already did write on SX minus, of course, is 1 over square root of 2, 1 minus 1. SX plus is square root of 1, 1. So you can multiply all this together. So this is H bar over 2. Now this is a 1, 1 multiplied by 1, 1. Put H bar over 2 outside. This will be 1 minus 1 multiplied by 1 minus 1. And if you multiply this together, what they will produce? This will be 1, 1, 1, 1, right? That will be that metric. And this metric will be 1, minus 1, minus 1, and no, 1, plus 1, plus 1, and did I get that right? Minus 1. No, I keep just 1, minus 1, minus 1, plus 1. That will be this, right? And if I add these two matrices together, then you can see there's a minus sign here. So this cancel out, this one cancel out. So minus minus, that's giving me plus 1, 2. So I'm able to write on this H bar over 2. And this is factor 0. And 1, 1, 0. Right? Did I get that? Everybody agree? I'm missing a factor of 2 somewhere. There's a factor 2 here. That's a factor 2 here. And then this will be correct. Yes. This factor 2 came from normalization. Square root 2. Square root 2 contribute from this factor, square root 2. That's okay. Yes?
Is the order of the matrices in that second part wrong?
Huh?
Because is it supposed to be a row vector multiplied by column vector? Like for 1, negative 1, and 1, negative.
This one.
Okay.
It should be 1, negative 1, times 1, negative 1. Thank you. Very good. representation. This is Sx. You can do the same exercise, but I'm not going to do it. So Sy representation in matrix. This is of course h bar over 2, and the Sy plus minus h bar over 2, Sy minus Sy minus. Exactly the same procedure. You should be able to do it yourself. And if you multiply all this matrix together, you get s equal to h bar over 2. What do we want to expect? We get 0, I. The only thing different is that 1 here will be I, and this is I, 0, right? Well, in fact, if you do carefully enough, it just turned out to be minus sign there. So, to summarize, Sc is equal to h bar over 2, 1, 0, 0, minus 1. This is all in the eigenstate of Sg operator as a basis, right? So, and the Sx is equal to h bar over 2, and 0, 1, 1, 0. Sy is equal to h bar over 2, 0 minus I, 0. And we also write on this as x as a vector form, which means a 3-component, h bar over 2 sigma. So this we call sigma y, this we call sigma x, this we call sigma z. Those 3 matrices are called Pauli matrix. We often will use that notation. So Pauli matrix itself has this is the Pauli matrix. Has no dimension. Okay. The S, the spin would not be, of course, later on is part of the angular momentum, and so it's carried the units of angular momentum. H bar has the units of angular momentum. The Pauli matrix itself has no dimension. So that's so that's the basic representation. Now we have a matrix representation. Now we can easily to work out the commutative relationship. And from commutative relationship, we'll look at we're able to talk about uncertainty, the uncertainty relation between the observable. So we just already said an observable represented by by a matrix in certain basis. And if you do a measurement of particular observable, no matter what quantum mechanical state, we always collect to a eigenstate of the observable we are measuring. And we associate that with as a probability, as a certain probability. So in particular now, we have this matrix representation. Let's examine a little bit of the relationship between those observables. In particular, we define commutator. A commutator of 2 operator A and B is formally defined as A times B minus B times A. Right? And remember, observable represent the operator, the product of operator in general are not they are associated, but they cannot commute in general. Namely, you have to pay attention to order. So let's just in particular take the example of Sx and Sy operator. Let's evaluate the Sx and Sy combinated between Sx and Sy. Alright, now we know this. Each of them carry h bar over 2. Let's just take this h bar over 2 square to the outside. So that will be h bar square over 4. And this will be sigma x, sigma y, minus sigma y, sigma x, right? That will be just the. And this is relatively easy. So h bar over 4. Sigma x, we already say is 0, 1, 1, 0. small y is 1 is 0 minus I 0. And we do this 0 minus I. And some of you probably fast enough to carry out this product. And whatever you y over 4. What would I get? So let's say 0 multiply this together, so 1, so this will be I, and this will be 0, this will be 0, 1 will be 0, so this will be minus I, right? That's the first product. The second product, we do the same thing, 0, so this will be minus I, 0, 0, this will be I. Yeah? You agree? Therefore, and add this together, this is in fact exactly the same, so I get factor 2, so I'll get h bar square over 2, and in fact I'll get I factor outside, so this is equal to I h bar over 2, and I'll get 1, 0, 0, minus 1. Okay? Everybody follow? Yeah? And now I can h bar over 2 times this. What is this matrix? This is sigma z, right? Notice this is sigma z. So therefore, this in fact equal to I h bar over 2 sc.
Should it be I H first?
No, without 2. Yeah? Good? Is that good? So I h bar times sigma z. So if you see commutative between x and y is producing. In fact, you can go now verify all the commutative relationships in general. You can write down that Si, Xj, I running through xyz equal to I h bar epsilon I j k sk. Now here's the notation. Epsilon I j k, what do we call complete anti-symmetric unit tensor, and this is defined as is equal to 1 if I j k is equal to 1, 2, 3 or permutation or cycle. So 1, 2, 3 this will be 1. If I have 2 cycle, this will be 2, 3, 1. And one more cycle, this will be 3, 1, 2. So 1, 2, 3, 2, 3, 1, 3, 1, 2. They are 1. It will be equal to minus 1 if I permute toward this indexing. So like if ijk is equal to like 2, 1, 3, for example. Permute the 1, 2. And then any cycle bit, so this will be 1, 3, 2, and 1, 3, 2, and 3, 2, 1. And with 0, everything else, if I equal to j, or j equal to k, or I equal to k. If any two indexing are same, it will be 0. Okay? And they are not, if they are distinct, they depend on whether it is cyclic computation of 1, 2, 3, or anti-cycle if you can prove that. That is epsilon I j k, is a useful for mathematical entity. This is turned out to be beginning of that. This is show that xx and y does not commute. See, xx and y, the commutator between the two is non-zero. That's what we will call this two operator, or two observable if they are associated with observable, as a incompatible observable. So this shows xx and xy are not compatible observable. Namely, they cannot be observed simultaneously to the precision. Okay? You cannot produce a state which is a simultaneous eigenstate of both x and sy. And in fact, so we're going to now generalize this because formal definition. So formal definition say if A and B is equal to 0, we say A, B are compatible. And that would later on imply that we can have simultaneous eigenstate for A and B. And if this is not equal to 0, we say incompatible. So two observable are either compatible or incompatible. Now we have a very important theory, fundamental theory. Which say if A and B compatible, compatible observable, and if A, B are compatible observable and eigenvalue of A are non-degenerate, and the eigenvalue of A are non-degenerate. Non-degenerate, remember, means that all eigenvalues are distinct. We don't have two eigenstates, we have the same eigenvalue. So under that condition, then A prime B operator A prime are diagonal. Well, let's say is diagonal. Now obviously A is already diagonal. Operator A is already diagonal in the basis of its eigenstate. And here basically say if A and B are compatible, namely the commutator between them are 0, then B operator in the basis of the A eigenstate is diagonal. That means it's only diagonal matrix elements. Namely, this would be 0 unless A prime equals A double prime. A prime is A double prime. Or we can say A and B can be simultaneous, can have simultaneous eigenstate. Can have all. So this is one way to say all A, B have simultaneous eigenstate. Okay, so if two observable are compatible, we can have simultaneous eigenstate. We can have simultaneous eigenstate. So that means, of course, that I can find the eigenstate, and I can label the eigenstate such that that's the following, that they can be written as a simultaneous eigenstate of the A and the B operator. So that means in general, I can have a state which labels eigenvalue A prime, B prime, and if A operating on this would be producing A prime value, and the B operating this. So this would be equal to B prime. Okay? And in fact, A prime, it will be simple, and of course, so I can label the eigenstate now with 2 in this, if they're simultaneous eigenstate. And this can be generalized to more than 2 operators. In fact, if I have, and this, so generalized. So if I have an operator A commute with B, and a B commute with C, and a C commute with D, and so on and so forth. I have number of operators which commute, and they're all equal to 0. Then I can find the simultaneous eigenstate for all of them. I didn't show the theory. Okay, let me prove the theory first. If I generalize this, let's prove the theory. Well, I think that proves that B has to be diagonal. Why B has to be diagonalized? So let's do the following. Let's calculate this quantity, because let's calculate this quantity. A double prime, A B commutator, A prime. If A, B are compatible, we know that equal to 0 on one hand. That's equal to 0. Equal to 0. And then I can now expand this. I can write on this A double prime, A B operator. And the minus B A operator. This is formal definition, right? This is formal definition of the commutator relations. Now, on the first term, I'm going to operating A to the left. A to the left, okay? Now, A and B are observable, remember? They are observable, that means they are Hermitian, right? They are Hermitian. So when we say A prime equal to A prime, what would I get? Would I get A prime operating A? Because if I take dual, this thing will be A dagger, right? A dagger. But because A is a Hermitian, so A dagger saying as A, so I can write it this way. So that's equal to A prime. This in principle is A prime is star, right? If I take view of that, a number go to star, right? So therefore, but remember the eigenvalue of the Hermitian operator we said earlier from last lecture are real, right? The eigenvalue are real. So therefore, if I operate now A on the left, this will produce, of course, A double prime, and this will be A double prime and B, right? And this time I'm operating to the right, I'll get B A prime and A prime, right? I will get that. Yes.
I'm sorry. The A double prime and A prime. Do those mean eigenstates?
They are
of A?
eigenstate of A operator.
Okay.
They are eigenstate operator. That's the visual notation. They are eigenstate operator. So, and now this A prime, A double prime, of course, a number, so I can pull it out. So therefore, this will be here. This will be equal to A double prime minus A prime. Factor out, this will be A double prime B, A prime. And then we know this is equal to 0 according to what we started. We'll start here. 0. So you can see if A prime are not equal to A double prime, if A prime not equal to A double prime, then this must be equal to 0. And that shows, that's basically what we say here. A prime, this major element, A double prime, B, A prime, has to be diagonal. So if the two observable are compatible, they have simultaneous eigenstate. So now after done that, I come back to this statement. I'm going to generalize to many observables. So in general, I could have this, then I could have. In general, you have more. I have A prime, B prime, C prime, da da da. In general, this will be A prime, B prime. So you're going to have a simultaneous eigenstate of all this operator. The same thing. So, and the same thing. So basically, if I have a set of an observable which commute, then I should be able to find an eigenstate which is a simultaneous eigenstate of all the operator which commute. And in fact, now you go back to quantum mechanics in undergraduate class. You remember hydrogen atom? And you look at the energy level, it actually can be classified into different N and L and M. And some of them are commute. So Hamiltonian, for example, commute with total angular momentum. So so it can have simultaneous eigenstate of Hamiltonian and L. And the L and the Z component, the angular momentum and the Z component commute. So in fact, you can have simultaneous eigenstate as N, L, and M. So we'll come back to talk about that. More complex. Okay.
Excuse me,
Yes.
I have one question. That last line on the left, you have a double prime bra multiplied by a double prime. Based on what you said over there, shouldn't it be a double prime star, or am I missing something?
Very good question. Yes. So that should be a double prime star, right? Now why am I able to write? Why would I able to write it as
It's
a double
real.
prime?
It's real.
It's a real prime because they are observable eigenvalue of observable are real. This means pay attention. Okay. And then we have a complete relationship, which we earlier we say we have complete relationship we write on this way. Right? This is equal to 1, given a set of eigenstate. Now if I now have a set of operator commute, okay, then some of these eigenstate may be degenerate, some not. So in general, this will be generalized to A prime, B prime, all the distinct kind of labeling, or distinct labeling. This will be general complete relationship as well. So maybe if I use just one observable, I don't have enough labeling. I mean, some will say have same A prime value but different B prime value. Those are labeled distinct state. So you need a complete set. So the completely this relationship in general and is written this way. It's a sum over a complete set of compatible observable. Okay. Now that is all good. Now what if this is a compatible observable? What if it is incompatible observable? And we already see the incompatible observable example. Like x and sy, for example, we did the example earlier, they are not compatible. They are not compatible. And in fact, let me come back to Stern-Gerlach experiment to reiterate now what happens is incompatible observable. Let's imagine I have I do a measurement on A. I in general can be using all the possible eigenstates. Let's say pick a particular eigenstate, A prime, and then plot the rest. Just pick. So I know my quantum mechanics state is a particular eigenstate of A observable. Now imagine I take this and I do a B measurement. Well, actually, let me do one of the first. Let's say I do this, and then I do C measurement. Okay? C measurement. And then I know I want to know what's the probability I get this particular state C prime. What is, given the fact that I know the starting state is A prime, I do a C measurement. What is the probability that I'll find the state is a C prime? What is that probability? So this is a probability of, given I know it's A prime, what is C prime? How would what is the mathematical expression for that? I kind of briefly mentioned it earlier when we tried to explain the meaning of it. Yes?
Is it the absolute value expectation of
Absolute value of?
ket C bra A?
Bra
Or
first.
bra C,
Yeah.
right?
Bra what? C or A? C prime and A prime. Square. So this, remember, this you say is probability of finding C prime state in A prime state. That's what I'm looking for. Given that fact I know it's already in A prime state, what is probability of finding C prime? So that is what that's the formula that is that expression. Now this expression, okay, that's good. And this expression I can write in following. Okay? I can do this, of course, is C prime and A prime. I'm going to in between C prime and A prime insert a complete relation of B operator. So this will be summing over B prime, and then I do this C prime, A prime, and then after that I'm going to insert another set of complete relations, which is B prime. So B C and so I have this A prime, and then have A prime, B prime, double prime. I'm going to just call this C for a second. Okay. This is just C prime over A prime, right? Because this is a complete relationship. Right? This is just A prime, C prime, because I insert another complete relationship. Okay? So that is a square of mean. Square is this complex conjugate of that, which I basically flip this one. Okay? Now, I'm delete for that moment. Now imagine I do following. I did exactly the same thing. A prime, I block the rest. But in between, I do a observable B. And I know this advantage of observability I make using a B prime value. And then from that, I do observable C, and then I get C prime value. Right? So now this is a different probability. This is probability is a given the A prime state with what is the probability of observed C type. But in between, I take a peak of a B observable. I don't care what value it is. I'm going to sum over all these things. Sum over all these things. Sum over all the B prime. I just want to take a peek what is the B value is. Okay? And then, independent of all this B value, I sum over all this. One would expect this and this. Classically, this makes no difference. I mean, I didn't do anything. I just take a peek of this and say what is B value. And doesn't matter what B value, I add up all the probability. So what is this probability? This probability is this let's call it Q. This Q. And still is given the A prime, and I want to put this one. But this I sum over all the B prime. Okay, I take a peek. So I take a peek. Namely, I give them A prime, and I want to observe the B prime. What is the probability of B prime? Well, this is the probability of given A prime that I take a peek at producing B prime. But I'm going to sum over all the possible B prime. And then after B prime, of course, and I want to take this. This is the property I'm looking for. Given the A prime star state with, I take a peek what kind of value is B prime. Doesn't matter what is B prime, I continue and I measure the C, what is probability of producing C prime. Classically, you expect this to be exactly the same as this, because I'm taking peek, and doesn't matter what value I count all the way. But you notice this expression is distinct from this expression, because if I write this expression out, it will look like this. Can you understand this? So let me make this understand what this is. So this is equal to sum over B prime, and so if I fold it out, this will be C prime, B prime, and the B prime, C prime, right? And this value will be B prime, A prime, and A prime, C B prime. And of course I can switch it order a little bit, so this will look like A prime, B prime, B prime, C prime. So this expression looks almost like this expression. And this expression it does not quite look like this expression. Did I miss something? No. Okay. Let me see what this. Let me write down this is C prime, E prime, and the B prime, C prime. And this will be B prime, A prime, A prime, B prime. And I want to write something which look like this expression. So I have C prime, B prime, which looks like this, and then I have B prime, A prime, B prime, A prime came from here, so I do have that. I have B prime, A prime, this one, okay? That's now look like this. And then I have here A prime, B prime, that's from this guy, and then B prime, C prime, which is this guy. So you can see this is exactly the same as this expression. This, the second term, it's not quite as same this time. Notice here is a sum over, that's another sum which sum over B double prime here. While here I only have one sum, which is sum over B prime. So that is a fundamental quantum mechanical. Namely, whether I take a peak of B or not, change the consequence of outcome. Change the outcome. And that's fundamental quantum mechanical. And quantum mechanical say, even though I have stayed here, whether you the mere fact you observe it, even though you don't do you didn't do anything with it, just simply observe what value of B is, you perturb the quantum mechanical state. The fact you did observation doesn't matter what you observe. The fact you did observation, it changes this quantum mechanical state. It changes the quantum mechanical state. So observation fundamentally perturbs the quantum mechanical state. That's something very important.
Can you point out again how that is shown in what you've just done?
You're from here, you?
I'm sorry?
What I show?
What you just said about perturbing a state.
Because you can see this expression, this probability P tilde is not same as this probability.
And what's the tilde mean?
Tilde, P tilde is I calculate the same probability except I take a peak of what B value is. Remember, notice this. This is a P tilde is given the A prime. I take a peak of what is B value is. That is this probability. And then independent of what this B value is, then I look at the C value and I sum over all possible B value.
In the first probability, though, you introduced the B value far on
In
the right.
the first, I introduced here a mathematical construction. I didn't do observation. So the first case, in fact, this is just 1. That's just a mathematical construction. It's a mathematical imaginary construction I do. Okay. So this is simply insert a completeness relationship. That is a problem. Yes.
So basically there, you put in an identity operator,
Yes.
but you had to do it twice, which is why you had 2 indices.
That's right, because I put identity here to make it look like this. And in order to make this look like, I need to put another identity here. And because it's identity relation, I put here, this is B prime, this is B prime, and the B prime. Now, I in general cannot do a B prime here, because B prime already used. So I need to use the B double prime to insert identity. While in this expression, you notice this is not B double prime, it's B prime. So this, you cannot simply absorb this identity relationship because there's another B index in here. If this is the B double prime index, then you absorb this into completeness. So this is what fundamentally shows that this probability is different from that probability. And the difference between this is I actually did observation in the middle. I observed what is possible B value. And that fact that we did observation, that changed the quantum mechanics state. So that is a very fundamental quantum mechanics. So we have quantum mechanics, quantum mechanics state are quantized, right? And number two, when we make observation on quantum mechanics state, it collapses into eigenstate of that observable. That's number two. And this is number three, very important qualitatively. Any kind of observation you on quantum mechanics state is perturbed quantum mechanics state. Observation perturbed quantum mechanics state. That's why chemistry we say, okay, we do this experiment and try to verify this. Quantum mechanically, there's no complete verification, because every time you do measurement, you are doing observation. And if I do observation, I get some result, and you do the observation, fundamentally that's a different observation. Right? So that's no exact identical thing. Of course, ideally, you can imagine that way, but fundamentally, the quantum mechanics state is always involving the fact at this moment that you and me together, universe is presented by a quantum mechanics state. The next lecture I come by, even though you sit exactly the same position, I can talk about exactly the same lecture, it's different quantum mechanics state. Different quantum mechanics state. All right. Now, so that's the qualitative. Now, quantitatively, then if the two observables are not compatible, then we have this fundamental mathematical construction called uncertainty relation. So if the two observables are incompatible, namely the commutator, same. Now this whole probability, the fact is P2 is not same thing. You can show, which I'm not going to do, if the B and the C commute, or if A and the C commute, then you can show these two probabilities are actually the same. Namely, if they are compatible, observable, then it doesn't matter. Right? So only if they are incompatible.
Question?
Then, yes.
Did you say that if B and C commute or A and C commute?
Oh, A and B, if any of those two commute,
yeah, so
that's good enough.
One of them has to commute with B, and then it's fine.
Yeah, that's
okay.
Fine. Then it's fine.
Thank you.
Well, because once you commute, then the sequence is no longer important. And then you can show. I'm not going to show that, but mathematically you can show it. Now I'm introducing uncertainty relationship. To introduce uncertainty relationship, I first need to use another uncertainty. Let's first introduce the so-called variance. Okay. We define a measurement. Measurement is of quantity. We already defined. The expectation method is this now alpha. Now this refers to some arbitrary state. Some arbitrary state. So that's expectation value. Variance of measurement. Variance is defined as delta A. The expectation of delta A square. Delta A is formally defined as, of course, as A minus A expectation value. And sometimes we just, for simplicity, we just write on A bar as expectation value. But this usually means this, okay? So this variance is this. This is called delta A, and a square with this, and then take the expectation value. That's what we call variance. Variance. And of course, you can expand this thing. So this is of course is A squared minus A bar. Now A bar already is a number. Remember A bar, just be emphasized. A bar is already a number. So and then this expectation value. Now of course this will be expectation value A squared. This is number, so this will be expectation value of A, expectation value of A, and then of course And these two are same quantity, is the plus sign here. I should have two factor here, two factor here, two factor here. So therefore this is equal to a squared minus expectation of a n squared. So variance is variance formally is defined as variance. Okay, with that defined, then here is uncertainty relationship. If the two observable are compatible, incompatible, namely the commutator is not equal to 0, then take some arbitrary quantum mechanics state, doesn't matter what state are on this, because arbitrary quantum mechanics, that's why we just write in this way without emphasizing alpha. This is this. So then we have this uncertainty relation for any A, B operator, delta A square expectation value, the variance of A and the variance of B, and the B square expectation value is greater equal to a quarter of expectation value of commutator between A and B, and then square. Okay, that is a uncertainty relation. Namely, and of course, you are familiar with that we know the x coordinate and the momentum, they are not compatible observable. X and p, so example is x and p, commutator of that in fact is I bar, and so delta x squared, delta p squared is greater equal to h bar over 4. Or we just did that as x and as y. We show this is equal to we show that earlier. This is equal to what? This is equal to I h bar s z, right? We show earlier that the s x s y commutated between x and y is I h z. So you can see, no matter what state, delta s x, delta s y, and this would be greater equal to h bar squared over 4. But this will be h squared, so h bar squared over 4, and the expectation value of SC squared. Right? That would be an example of that. So go ahead. That example somewhere. Yes. And in fact, this there, a good exercise to calculate this quantity as an example. Can we calculate that quantity? Let's take the example. Let's say SC square in positive. Both my alpha is positive. What this equal to? Anybody?
H bar squared over, yeah,
H
H
bar
bar squared
squared
over 4.
over 4, right?
Yeah.
The reason for that is, what is the reason for that? Why?
Because that's an eigenstate, so we
So
get.
this is eigenstate with h bar over 2 as eigenvalue. And you do it again. So this is h bar squared over 4. Now what about this?
Same thing.
Same. And in fact, it's plus sign because minus h bar over 2 and it's multiplied by 2 and 4. Now what about this? Anybody else? Anybody else? What about this? Yeah?
Would be negative
You think into the next square, how will you get that result? So let's do it step by step. So plus, let's do SC, and one SC operating on minus will give me
Isn't it just negative h bar over 2?
next power 2 and 1. Yeah?
Yeah.
Now, negative h bar over 2 can be taken out. Yeah? Write down negative h bar over 2 out. Okay, now what is this one?
0.
0. So in fact, this whole thing is 0. Yeah?
And that line up there with the delta sx squared, delta sy squared, should there be a delta in front of that sc squared?
Delta s squared, delta s squared.
Should there be another delta in front of this?
No, it's a combination between A and B. Expectation.
Oh.
This is B. Just a second. Wait a second. Combination squared. Expectation values. Wait a second. Just give me a second. So, yeah, so therefore now we can do this quantity. We can just verify this uncertainty condition. That's, and obviously same thing. It's minus and c squared and 0. So let's say now I what is delta x squared? Delta x squared will be alpha and sc squared minus sc expectation value squared and alpha. Right? That's a formula with delta x squared is. Well, now I just say, so this is breaking into alpha sc square alpha minus sc square sc expectation value square alpha, right? Is that? Agree with that? Yeah?
Should there be an SZ because you were SX and then you started?
XX, I'm sorry. Oh, let's just do SC. Yeah. And we just show that this is equal to the fact that I show plus, if the plus actually h bar square, minus h bar square, and it's plus equals minus 0, minus plus equals 0. Would you accept my certainty, my assertion that for arbitrary alpha this is h bar square over 4? Do you agree with that? Because alpha arbitrary state is a superposition of plus minus state. Is some arbitrary superposition of our state. And if it's plus I give h bar 4, the plus term goes to 0. So in fact only the diagonal term remains. So I get it. So this will be given that. And of course alpha is normalized. As z expectation value, now this of course it must depend on what is alpha state is. Suppose my alpha is x for example, is 0. If my alpha is plus state, this will be h bar over 2 and so on and so forth. So that actually is so. So let's just say alpha is plus. Now in this case, this would be h bar square over 4. This would be expectation that this would be h bar square over 4, and that would be 0. So that's the one possibility. You can do the same thing whether you do x or y or z, the component based on. The bottom line is you should be able to calculate any of this quantity. If I give you some arbitrary alpha state, and tell you alpha state is the superposition of some plus and minus state, you should be able to verify. So you can, in fact, take any kind of alpha state and then verify, can calculate it as x squared, as y squared, and then verify that uncertainty relationship. We'll come back, of course, to formally prove that uncertainty relationship is indeed can be derived or journey. So I'm going to show that in next lecture on the uncertainty relationship. And it's actually just a few minutes mathematical trick to show that this is a very foundation relationship for quantum mechanics. So we have today's what we said important is the measurement of the quantum mechanics state is observable and compatible. Then they have to satisfy uncertainty relationship. And this, of course, physically means that variance essentially means how accurate you can measure some quantity. Larger variance, that's more larger uncertainty. And so therefore, if two observable and compatible, they cannot be measured simultaneously to a very small variance. But they have to satisfy an uncertainty relation. All right, that's the all. First, the recording part is stop.